This video is about rate laws. By the end of this video, you should understand what information can be obtained from a rate law. You should be able to recognize the parts of a rate law. And you should understand the difference between zero, first, and second order reactants. There are two types of rate laws that we're going to study in this course. The first is the differential rate law. This shows how the rate depends on concentration. This is the most commonly used rate law, therefore it's usually just called the rate law rather than the differential rate law. We're going to look at this one in this video. In a future video, we'll look at the integrated rate law. This shows how concentration depends on time throughout a reaction. Recall from a previous video that we saw that the rate of a reaction changes as the concentration of the reactants change. Generally, the rate will decrease as the reactant concentration decreases due to the smaller number of molecules, which leads to fewer collisions. So our rate law, as we just said, will focus on the relationship between the rate of the reaction and the concentration of the reactants. If we have a reaction, A plus B yields C, our rate law can be written as follows. Rate equals K, which is our rate constant, times the concentration of A raised to some power times the concentration of B raised to some power. N and M here represent the orders of the reactants, which we'll discuss a bit later in this video. It's important to note that K, N, and M must be determined experimentally. You can't simply look at a reaction and its stoichiometry and determine values for K, N, and M. In a future video, we'll talk about how to determine K, N, and M. Now let's look at each part of the rate law individually, starting with the rate constant. Again, K represents the rate constant. The rate constant is essentially just the proportionality constant between the reactant concentrations and the rate. We know that the rate will change proportionally with the reactant concentrations. So K is simply the constant that will make that proportionality hold. K will vary widely, so don't worry if you have a very small k, like a fractional number, or a k in the thousands. That's totally reasonable. K also changes significantly with temperature and with the presence of a catalyst. It's also important to note, though, that the reactant concentrations do not affect K. Therefore, as the reactant concentrations change, only the rate will change, not the value of K. The reaction orders now, which are represented by M and N, these describe the effect on the rate of the concentrations of each reactant. In this class, we'll only look at zero, first, and second order reactions, though there are plenty more. The order can be different for each reactant, meaning the reaction might be first order in reactant A and second order in reactant B, or zero order in reactant A and second order in reactant B. One does not determine the other. Looking at this simple rate law, we can consider what is meant by zero, first, and second order reactions. A zero order reaction tells us that changing the concentration of the reactant will not affect the rate of the reaction. So if we study the rate of this reaction at various concentrations of A and find that there is no relationship between the rate and the concentration of A, we know that this reaction is zero order in A. This makes the value of M 0, and as you know, when you raise something to the 0 power, it just becomes 1, which holds with the idea that rate is not related to the concentration of A. A first order reaction means that the rate is directly proportional to the concentration of A. In other words, if we double the concentration of A, we double the rate. If we triple the concentration of A, we triple the rate, and so on and so forth. Here, the value of M would be 1, therefore A would be raised to the power of 1, which holds with the idea that doubling A doubles the rate and tripling A triples the rate. Finally, a second order reaction is a reaction in which the rate is proportional to the square of the concentration. So, if we find experimentally that doubling the concentration of A will quadruple the rate, then we know that the reaction is second order. M here would have a value of 2, meaning the concentration of A is squared. Occasionally, you might be asked to consider the overall reaction order. This is the sum of the orders for each reactant. Since this rate law only contains one reactant, it would simply be the value of M. But if there was another reactant, say B, as in the previous rate laws we looked at, you would add the order of A and the order of B to give the overall order of the reaction. Just to make sure you have all this information straight, pause the video here and answer the questions about the rate law shown. When you come back, I'll reveal the answer. Welcome back. Here's what you should have gotten. Returning to the rate constant for a second, it is important to put units on your K value. However, the units will depend on the overall order of the reaction, so the units on K will not be the same for every rate law. You can determine the units on K using algebra. Consider the rate law shown here. We can do this by substituting the units for each variable into our equation. So we've replaced rate with molarity per second, or molarity times second to the negative 1. This just means seconds is in the denominator when it's raised to a negative power, equals K times molarity, because that's the unit of concentration here. Solving for the unit on K, then, we divide both sides by molarity, and we get K is equal to seconds to the negative 1, or 1 over seconds. Pause the video and try to solve for the unit on K in this rate law. When you come back, I'll reveal the answer. Welcome back. You should have gotten a unit for K equal to 1 over molarity times seconds, or molarity to the negative 1 times seconds to the negative 1. Finally, let's try one more practice problem. Pause the video here, read and answer the question, and when you come back, I'll reveal the answers. Welcome back. Here's what you should have gotten. The rate law is listed here from the information in the problem. The unit on the rate constant comes out to be 1 over molarity squared times seconds. And here we see that the third box represents the fastest reaction, since we already saw that the blue spheres representing B have the greatest effect on the rate of the reaction, because the reactant is second order with respect to B. In other words, if we double the amount of B, we will quadruple the rate. So the more B, the greater the effect on the rate. That brings us to the end of this video. Let's review our goals. First, we looked at what information can be obtained from a rate law. Then, we learned how to recognize the parts of a rate law, including the rate constant and the orders of the reaction. And finally, we looked at the difference between 0, first, and second order reactants.